and welcome. I am so happy you're here with me today. In our last video, we explored some of the fundamentals of movement, how every action begins with a push or a pull, how stability is guided by our center of gravity and base of support, and how our bodies function like an incredible system of levers and pulleys built for both strength and speed. It was such a powerful reminder of the hidden mechanics working inside us every single day, building on that foundation. Today I want to take you a step further. Have you ever stopped to think about the sheer magic of movement, whether it's lifting a coffee mug, going for a gentle walk, or pushing yourself through an intense workout? Our bodies are performing the most incredible symphony of actions. And at the heart of that symphony are our muscles. Today, I want to pull back the curtain and show you the beautiful science of how our muscles work. We're going to explore the building blocks of strength, endurance, and motion. And I promise, by the end of our chat, you'll look at your own body with a whole new sense of wonder and appreciation. Let's begin with a fascinating fact. Your muscles are not all the same. They are actually composed of different types of fibers, each one a specialist designed for a specific job. Think of it like having a team of different athletes inside every muscle. First up, we have our type I fibers. I like to call these the marathon runners. Their technical name is slow twitch, and they are built for endurance. These fibers are deep red because they are packed with myoglobin and mitochondria, which are structures that use oxygen to produce energy. This is called aerobic metabolism. They contract slowly, but they can go and go and go for a very long time without getting tired. You find a lot of these fibers in the postural muscles of your neck and back, working all day to hold you upright. Next, we have the type II fibers. These are the all-rounders of the muscle world. They are a beautiful blend of power and endurance. They are also aerobic, meaning they use oxygen, but they contract much more rapidly than the type I fibers. They are pink because they have a good amount of myoglobin and mitochondria, but not quite as much as the marathon runners. These are the fibers you rely on for activities like walking and running. And finally, we have the powerful type IIb fibers. These are the sprinters or the powerlifters. They are white because they have very few mitochondria and myoglobin. Instead of oxygen, they get their energy through a process called glycolysis, which is anaerobic. It doesn't need oxygen. This allows them to contract incredibly fast and with immense force. The trade-off? They get tired very, very quickly. You use these for short, intense bursts of movement, like lifting something heavy. Isn't that elegant? Most of our muscles are a mix of all three types, but the muscle's main job determines which type is most dominant. Endurance runners tend to have more type II fibers, while bodybuilders develop more of those powerful type IIb fibers. And here's the really cool part. With training, you can actually change their characteristics. Endurance training can encourage those fast-fatiguing type IIb fibers to become more like the durable type IIa fibers. Your body literally adapts to what you ask it to do. Now, it's not just the fibers themselves that matter, but also how they are arranged. The architecture of a muscle determines its shape and, more importantly, its function. Some muscles are called parallel muscles. In these, the fibers run parallel to each other like a bundle of uncooked spaghetti. This design is fantastic for creating a large range of motion. They can be long and strap-like the muscle in your neck, or spindle-shaped with a wide belly, like your biceps. Then we have the oblique or pinnate muscles. Imagine a feather. The short fibers attach to a central tendon at an angle. This clever design allows the muscle to pack in a lot of fibers, which makes it incredibly powerful. It produces more force than a parallel muscle, but it has a smaller range of motion. The deltoid muscle in your shoulder is a great example of this powerful design. And of course, we have circular muscles, which are arranged in a ring. They act like a drawstring on a bag, closing openings when they contract. The muscle around your mouth is a perfect example. So we have the fibers and their arrangement. Now, let's talk about movement itself. We use simple terms to describe how our joints move. Flexion is bending, extension is straightening, abduction is moving away from the body's midline, and adduction is moving toward it. You might also hear the term range of motion. Active range of motion is how far you can move a joint all by yourself, using your own muscle power. Passive range of motion is how far a joint can be moved with outside help, like a therapist gently stretching your arm. Passive range of motion is usually just a little bit greater than active. When we do create a movement, our muscles take on different roles, working together like a perfectly coordinated team. The main muscle responsible for the movement is called the agonist or the prime mover. It's the star of the show. Working against it is the antagonist. For the agonist to do its job, the antagonist has to relax and get out of the way. Think of your biceps and triceps. To bend your elbow, your biceps, the agonist, contracts, and your triceps, the antagonist, must relax. Then you have synergists, which are helper muscles. They assist the agonist, making the movement stronger and more controlled. And finally, you have fixators or stabilizers. These muscles hold a bone or a joint steady, creating a stable base so the agonist can work efficiently. They are the unsung heroes of movement. Now let's get into the nitty-gritty of how a muscle works. We often use the word contraction, but it's a bit more nuanced than that. There are isotonic contractions, where the muscle changes length. This is what we typically think of as exercise. It comes in two flavors. A concentric contraction is when the muscle shortens as it creates force, like when you lift a dumbbell in a bicep curl. An eccentric contraction is when the muscle lengthens while still under tension, like when you slowly lower that same dumbbell. Eccentric contractions are all about control, and interestingly, they are where your muscles can generate the most force. Then we have isometric contractions. This is when a muscle generates tension, but it doesn't change length and no movement occurs. Imagine pushing against an immovable wall. You're working hard, your muscles are firing, but nothing is moving. That's an isometric contraction. So, to recap the power ranking, for any given muscle, it can produce the most force eccentrically, lengthening, then isometrically holding, and finally concentrically shortening. Let's touch on two more brilliant concepts. The first is the idea of a kinematic chain. This just means that our joints are linked together. In an open chain movement, the end of your limb is free to move, like when you're sitting on a chair and kicking your leg out. In a closed chain movement, the end of your limb is fixed, like when you do a squat with your feet planted firmly on the floor. In a closed chain, movement at one joint will always cause predictable movements at the other joints in the chain. The second concept applies to muscles that cross over two or more joints, like some of the muscles in your forearm that control both your wrist and your fingers. It's called insufficiency. Active insufficiency happens when a muscle is so shortened across all its joints that it can't contract any further. Try this. Flex your wrist all the way down and now try to make a tight fist. It's hard, right? That's because the muscles are already too scrunched up. Passive insufficiency is the opposite. It's when a muscle is so stretched across all its joints that it can't lengthen anymore to allow movement. Try this. Extend your wrist all the way back and now try to fully extend your fingers. You'll feel a strong stretch, and it's difficult because the opposing muscles are being pulled to their limit. Finally, when we put all of this into practice through exercise, our entire body responds. Of course, we build muscular endurance, the ability of a muscle to work over time, but we also improve our general body endurance, which relies on our heart and lungs. During exercise, your heart rate increases to pump more oxygen-rich blood to your working muscles. Blood flow is cleverly redirected away from organs that aren't essential at that moment, like your digestive system, and sent to where it's needed most. Your breathing becomes faster and deeper to bring in more oxygen and get rid of carbon dioxide. Your body temperature rises from all that muscular activity, so you start to sweat to cool down. It is a beautifully coordinated, system-wide response to the demands you place on your body. So, from the tiniest red and white fibers, to the way they are architecturally arranged, to the intricate teamwork they perform with every single movement, our muscular system is nothing short of a masterpiece. I truly hope this has given you a little glimpse into the incredible world inside of you, and perhaps a new appreciation for every step you take and every object you lift. I'd absolutely love to hear from you. What part of this was the most surprising or interesting to you? Do you have any questions at all? Don't be shy, let's chat about it in the comments below. Until next time, take wonderful care of your amazing body and stay curious.